Welcome to today's webinar. In the next 15 minutes, we will take a look at a small parameter that can have a surprisingly large impact, the polarization axis accuracy. So let's focus on the angle, how accurately the polarization axis is aligned to the defined reference edge or the marking. Basically, the key question is simple. What happens when the polarizer is good, but the axis is not exactly where the system expects it to be? Briefly about myself. My name is Friederike Maschak. I'm the head of marketing and sales here at codixx. If you have any technical questions or any commercial questions after this session, you can find my contact details here. Please feel free to reach out to me via phone or email, or just write an email to sales@codixx.de. My team will be happy to help you. Before we dive in, a little bit about housekeeping. Please keep your cameras and microphones off during the whole session to ensure a stable connection. If you have any questions, please post them in the chat at any time. I will address those at the end during the Q&A session. Please also note this webinar will be recorded and made available later on the codixx website. Any personal information, including names, chat messages, or participant details, like your picture or so, will be removed before publication and will not be stored any longer. All right, let's dive into the main topic today. So the challenge. So a polarizer is often selected by the wavelength range, contrast ratio, transmission, different dimensions which are available, or coating, which is a good way to start. But a polarizer is usually not an isolated component. It's a part of an optical system, which means it has to work with the system. It has to align with the sensor, with a wave plate, optical paths, a mechanical mount, the calibration model, or even sometimes with the manufacturing processes. So if the polarization axis is not exactly where the system expects it to be, yeah, you can have the best polarizer, but it still may introduce an angular error into your system. So it's always good for the whole system to also think of the polarization axis accuracy and the alignment to the reference edge, repeatability between parts, because tolerances can stack up in your optical path. So the main challenge, accuracy, is a small specification, but it can have a large impact on your system. So if we are talking about polarization axis accuracy, what do I mean? So the polarization axis defines the transmitted polarization direction of a linear polarizer. So in practice, this axis is usually referenced by a defined edge, a marking, a mount, or a system coordinate. And you have basically here in green is the polarization axis, which is marked on your product. For example, like in this picture here on the right, we have mounted color polarizers, which have these small white indents to mark the polarization axis. But there can always be an axis error, which defines the angle between the marked polarization and the actual polarization axis, which could be slightly different from the one that is marked. And this is a problem because if the reference is wrong, the system may calculate, measure, or calibrate based on a slightly wrong assumption. So the axis is not just a visual marking, it's an optical reference which is used by the whole system. Another point, also why it matters, like I said before, tolerances stack up. So in the real optical systems, no error comes alone. So the polarizer has a tolerance. This is just a sample setup. A wave plate, for example, has a tolerance. The sensor position has a tolerance. Mechanical mount, a software module, manufacturing processes. So even this software module assumes that all optical components are where they should be, and everybody comes with a certain tolerances. So and for the system in the end, only counts the total error. It does not really care which component introduces how much of an error. It only sees the total error. So, and within more accurate polarization axis, this could give you much more flexibility with other system or manufacturing processes. So it reduces one part of the tolerance chain and gives you more freedom in the remaining system. For example, here we have one version where the polarizer axis error is pretty large, which means everybody else in the system has to account for this to stay within the total tolerance budget. But if we can reduce the polarization axis tolerance or error, there's much more flexibility for all the other components. And depending on, this could have an influence on your budget, manufacturing processes, sourcing processes. So it's really something to take into account. So why does it matter? Also, contrast is directional. So you can have a high contrast polarizer with a wrong angle, and you still get a reduced system performance. Versus a high contrast polarizer with a correct angle, which has the usable optical precision. The contrast ratio is one of the most important specifications of a polarizer. The contrast is always connected to a direction. So let's refresh our fundamental physics with Mallow's law. So here you can see an ideal setup. You have your incoming light. You have one polarizer with a vertical axis and another one with a horizontal axis. So, and in an ideal system, as you can see here, this would equal to every the complete light being frost. So the intensity is 0. So, but as soon as we slightly deviate by an angle, the transmitted intensity increases by sinus squared. So even at very small angles, this effect is easily underestimated. A 1 degree error sounds negligible, but due to the quadratic relationship, we end up introducing a constant background noise that severely limits your sensor's dynamic range. So the polarizer itself may still have excellent contrast, but the setup doesn't fully use it. So this is especially important in systems where low residual transmission matters, extinction measurements, optical isolation concepts, polarimetric measurements, or any applications where a small intensity differences are interpreted as meaningful signals. So in practical sense, the contrast tells you how well the polarizer can separate polarization states. Axis accuracy helps to ensure the system actually uses the capability of the intended direction. And also the polarization axis accuracy has an influence on the measurement reliability. So the axis accuracy supports more reliable optical measurements, better comparability between devices, lower calibration uncertainty, reduced need for repeated adjustments, and also for stable reference conditions. So looking at this graph down here, there's an important practical distinction when characterizing a component in a lab by rotating it. You often see an offset at the minimum. Part of this is the finite contrast of the polarizer, but in a static setup, an axis error will worsen this background lead. So we will need highly reliable part-to-part, repeatable measurements across multiple devices without needing to manually calibrate every single system. So, which is why the accurate polarization axis alignment supports repeatability, both in the lab and later on in production. Another good example for an application of a higher polarization axis accuracy would be the Stokes analyzer. So this is a system that measures the polarization state of light and can calculate parameters like the state of polarization, degree of polarization, or the polarization direction. And if the polarizer axis is so the polarizer axis is part of the calculation model, which means if you have a wrong axis, you have wrong input into your calibration. So you can see here this Poincare sphere, which is used to visualize the Stokes parameters, and they are collected so you have these random light coming in. You have a wave plate and then a linear polarizer to get a certain polarization, which are then measured and used to calculate a certain measurement point on the sphere. If you have a polarizer with a faulty orientation, the system for the calculation assumes different parameters, which results in a different point. So basically, if the analyzer angle as mathematical reconstruction model is assumed to be at 0, but the real filter is actually at 0.8, this leads to the faulty projection on the Poincare sphere. And this results in a systematic error. It's a systematic error manifests as a rotation of the measured state of polarization around the S3 axis for the linear errors. So this is a simple but important point. The software calculates based on an optical setup. It assumes, but if the reference angle is wrong, the output can be wrong in a system. Another example would be polarimetric calibration. A calibration setup often uses polarization state generators on one side and a polarization analyzer on the other side. So the generator creates a defined polarization state and the analyzer measures the output of the optical system. So both actually depend on accurate polarization alignment, because if the generator is slightly wrong, the input state is not exactly known, and if the analyzer is wrong, the output state is not measured correctly. So this is why a high axis accuracy improves the trustworthiness of the calibration process. So both input and output reference depend, and there's also the question, which one do you trust? The polarization state generator or the analyzer? And those are actually used in quite a lot of important systems like lithography for the calibration of polarized lighting systems, or in a solar telescope for a polarization calibration unit, or even in polarization, optical remote sensing for polarimetric calibration of a polarimetric imager. So for developers, if you're looking to test a system, to design a system, our recommendation is simple. Define the polarization axis requirements early. Specifies the reference edge or mounting reference, defines the required angle and the allowed tolerances for your whole system. Clarify whether the axis needs to be marked on the polarizer or on the mount. Of course, the other optical parameters are still important. Please also think about your wavelength range, contrast ratio, transmission targets, coating, handling, size, all of the other stuff. But if the polarizer is used as a reference component, so the calibration concept should also be discussed. And the best angular error is the one you don't have to debug later on. So define the axis early on, not after the prototype fails. So this is where actually polarizers from codixx are quite relevant because we are making glass-based decorrect polarizers, which can be customized for different wavelength ranges. We have a high polarization axis accuracy. We can customize the polarization axis. We're working for UV visible infrared, and we have a really robust glass type polarizer. And we even allow, on request, offer a polarization axis accuracy down to plus minus 0.05 degrees. So if you have any questions more on this or want to send a request, please visit our website or get in touch with our sales team. And then as a final note, so let's summarize. The polarization axis accuracy may look like a small specification, but in an optical system that depends on the defined polarization state, it can strongly influence real performance. It affects how well contrast is used, how reliable measurements are, how much calibration is required, and how repeatable the system becomes from one device to the next. So your main takeaway for today should be, do not treat the polarization axis as a minor mechanical detail, treat it as an optical reference. If you want to know more, if you're carving these big formulas, Stokes calculations, etc., we have a white paper available just on the topic on the characteristics of the polarization axis accuracy. You can request it from your sales representatives. You can write an email to sales@codixx.de. Or also, reach out to us and we will send it to you later on. So thank you for your attention. Now would be the time if you have any questions. Check the chat. Okay, I don't see any questions so far. Well, there were quite a lot of mathematics and physics today. If there aren't any questions,
I have one question.
yes.
Can I ask you?
Yes, please talk away. No need to type it now.
Thank you. Could you please send this presentation for us?
Yes, sure. Please, I think the easiest way would be, did you register your email when you signed in to the webinar? Otherwise, just send us an email to sales@codixx.de. And also, like I said at the start, this webinar is being recorded, so you can watch the whole webinar afterwards as well on our website. Yeah, but yeah, we can send it to you also.
I just tried to send my mail to the chat.
Yeah. All right.
Please.
Yeah, my colleague will pick it up and then we will send it to you.
Thank you.
Yeah, you're very welcome. Thank you for joining today. Any other questions? Anybody else needing these slides? Yeah, please feel free to reach out and we will provide it for you. Otherwise, and we have some other topics coming up. If you haven't heard enough today about polarization, you're in luck because I will do a second webinar today at 5:30 p.m. About polarization and its general applications, what you can do with polarization. It won't be hosted by codixx, so you don't find it on our website. It's hosted via our distributor in the US, Laser Components. You can scan here the QR code to register, or as well, my colleague will post the link for the registration also in the chat. Feel free to join. Otherwise, our next webinar from codixx will be on July 8th about polarizers in life science. We also have other topics planned for the rest of the year, from designing a system, high optical precision measurements, or stability of the polarization. Yeah, I think lots of different topics. If you have missed any of our previous webinars, you will find recordings of all of them on our website. Yeah, and if you have any questions, I know it has been a big topic. Please get in touch, reach out to us. Thank you again for joining us. Please feel free to get in touch. We look forward to hear from you. Thank you and have a good day.